Welcome to our lesson on the evolution of the idea of atoms and elements. In this video, we will trace the history of how humanity went from basic philosophical questions about matter to our modern quantum nuclear model. We will examine how discoveries by pioneering scientists changed our understanding of the smallest building blocks of the universe. This journey will show you how science is a continuously evolving process of discovery. Let us begin our exploration of this topic. Let us review our learning targets for this section. By the end of this lesson, you will be able to identify and explain the key discoveries that led to our current understanding of atomic structure. You will also describe the major contributions of scientists like Thomson, Rutherford, Bohr, and Erwin Schrödinger. Finally, you will be able to illustrate and explain the modern nuclear model in your own words. Today, our primary focus is on the second question, which is highlighted on your screen. What key discoveries led to our current understanding of atomic structure and its subatomic particles? Let us find out how scientists unlocked these secrets. Let us examine this timeline of how our concepts of matter and atoms developed. It is amazing to see that this journey spans over 2 millennia. It started in ancient Greece around 450 BC, where philosophers like Democritus argued that matter consists of indivisible atoms, while Aristotle argued that matter is continuous. This timeline summarizes how our ideas about matter evolved over thousands of years. It starts with Democritus, who first proposed the concept of atoms. The timeline then moves to John Dalton and his atomic theory. The timeline continues through the discoveries of electrons, protons, and neutrons. This timeline is like a long relay race, where each scientist passes the baton of knowledge to the next. In 1808, English scientist John Dalton introduced his atomic theory. Dalton defined atoms as the indivisible building blocks of matter. At that time, chemists had identified around 30 elements. An element is a pure substance consisting of only one type of atom. Dalton's work marked the beginning of the modern era of chemistry, laying a solid foundation for atomic structure. Dalton viewed atoms as tiny, solid billiard balls that cannot be broken. Let us examine the core hypotheses of the atomic theory of John Dalton. He proposed that all matter is composed of extremely small, indivisible particles called atoms. He hypothesized that all atoms of a given element are identical in mass and properties, whereas different elements have different types of atoms with different masses. Furthermore, Dalton stated that chemical compounds are formed when atoms of different elements combine in simple, whole number ratios. Finally, his theory explained that a chemical reaction is simply a rearrangement of these indestructible atoms. Think about how Dalton was able to predict these tiny, invisible particles using only basic laboratory mass measurements. It is a testament to the power of logical thinking. On this slide, we examine 2 fundamental chemical laws that Dalton used to build his atomic theory. The first is the law of definite proportions, which is the rule that elements combine in fixed, constant mass ratios. For example, any sample of carbon dioxide always contains the exact same mass ratio of oxygen to carbon. The second is the law of multiple proportions, which is the rule that elements combine in simple whole number mass ratios. These laws prove that matter is made of distinct, individual atoms. This slide compares 3 major milestones in the evolution of the atomic model. It started with the J.J. Thomson model in 1897, which viewed the atom as positive matter embedded with negative electrons. Next, in 1911, Ernest Rutherford discovered the small, dense nucleus, proposing the nuclear model. Finally, in 1913, Niels Bohr introduced orbit paths, showing that electrons move in fixed, concentric energy levels around the nucleus. To understand how subatomic particles were discovered, we must look at J.J. Thomson's cathode ray tube experiment in 1897. Thomson noted that the Dalton's billiard ball model of the atom, which describes atoms as tiny, indivisible, solid spheres, did not include the idea of charge, and he theorized that the electrons must be within the atoms of elements.
The cathode rays experiment begins with a special glass tube containing very little air. Inside, 2 metal plates called electrodes are placed the anode and the cathode. The anode is connected to the positive side of a high-voltage battery, and the cathode to the negative side. Normally, electricity flows through a conductor, but here, metal electrodes carry the current through low-pressure gas. When the battery is switched on, an invisible ray shoots from the cathode toward the anode, traveling in a straight line. Scientists were puzzled. They knew something was coming from the cathode, but had no idea what it was, so they named this mysterious discovery cathode rays. J.J. Thomson repeated the cathode ray experiment, but added 2 charged plates, one positive and one negative inside the tube. When he switched on the battery, he noticed something surprising. The cathode rays bent toward the positive plate. This meant the rays were made of tiny negative particles. Attracted to the positive charge, Thomson realized that if these particles came from the cathode, then atoms must contain negative particles. He called them electrons.
In 1911, Ernest Rutherford conducted his famous gold foil experiment in his laboratory. He fired a beam of heavy, positively charged alpha particles at a thin sheet of gold foil. Based on J.J. Thomson's model, he expected the particles to pass straight through. Instead, some alpha particles deflected at sharp angles, and a few bounced straight back.
Ernest Rutherford conducted a groundbreaking experiment using a thin gold foil, a radioactive source emitting alpha particles, and a circular screen coated with zinc sulfide. Whenever an alpha particle hit the screen, a tiny flash of light appeared. Since gold foil is made of gold atoms, Rutherford expected the alpha particles to pass straight through. Most did, but some slightly deflected, and a few bounced back almost completely. This led to a shocking discovery. Atoms are mostly empty space, allowing particles to pass through. Some deflected because the atom's positive charge isn't spread out. It's concentrated in a tiny area. When an alpha particle hit this small, dense center, it was repelled and bounced back. From this, Rutherford proposed his atomic model, a tiny, dense, positively charged nucleus at the center, with electrons orbiting around it, just like planets around the sun. His model revolutionized our understanding of atoms.
Let us look closer at the gold foil experiment conducted by Ernest Rutherford. On the left side of your screen, you can see the expected result based on the plum pudding model, where particles pass straight through with almost no deflection. In the middle diagram, you can see the actual setup. A radioactive source fires a beam of alpha particles, which are heavy positively charged helium nuclei, at a sheet of gold foil. Surrounding the foil is a zinc sulfide screen, which is a detector that flashes when struck by radiation. Most particles pass straight through, but occasionally some experienced major deflections and bounced back. This proved that the positive charge is not spread out, but is packed into a tiny, dense, positive nucleus. In 1913, Danish physicist Niels Bohr refined the atomic model by introducing quantum theory. He proposed that electrons orbit the nucleus only in specific, fixed energy levels. We define energy levels as specific regions where electrons can exist without radiating energy. Electrons can jump between these levels, absorbing or releasing energy as light. This brilliant concept successfully explained the hydrogen emission spectrum and laid the groundwork for modern quantum mechanics. In 1926, Erwin Schrödinger developed the wave mechanical model, which is our modern quantum model of the atom. Schrödinger realized that lightweight electrons do not behave like tiny planets orbiting a central sun. Instead, they behave like waves of energy. Because of this wave nature, we cannot track their exact paths. Instead, we can only calculate the probability of finding an electron in a specific region, which we call an orbital. We define an orbital as a region where an electron is likely found. Think of this cloud like a rapidly spinning fan. You know the blades are there, but you cannot point to their exact location at any 1 millisecond. Think about how this probability model changes our view of physical boundaries. In 1932, English physicist James Chadwick made a monumental discovery that completed our picture of the atomic nucleus. While Ernest Rutherford had identified the positive proton years earlier, scientists noticed a massive gap in atomic weight. Chadwick confirmed the existence of the neutron, which we define as a neutral subatomic particle with no charge. This discovery explained the missing mass of the atom and solved the mystery of how positive protons can tightly pack together without repelling each other. Let us summarize the core features of the modern nuclear model of the atom. First, we must remember that most of the atom is empty space. Second, the atom is built from 3 subatomic particles: protons, neutrons, and electrons. The protons and neutrons are tightly bound together in the central nucleus, which is incredibly small and dense compared to the rest of the atom. Ordinary hydrogen is the only exception, as it contains 1 proton and 0 neutrons. Finally, the negative electrons form a cloud around this nucleus, moving in specific orbital paths called shells. Each of these shells can only hold a specific number of electrons. Imagine the nucleus as a marble in the center of a massive sports stadium. The empty stadium represents the rest of the atom. Next, let us discuss isotopes in chemistry. While all atoms of a specific element must have the same number of protons, their neutron count can vary. We call these variations isotopes. For example, hydrogen has 3 isotopes. Hydrogen-1 has no neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. All 3 isotopes behave the same chemically, but they have different masses. Isotopes are formed through nuclear reactions inside massive stars. Let us test your understanding with a quick pop quiz on isotope structure. The question asks us to find the number of protons, neutrons, and electrons in a neutral calcium-40 atom. By looking at the symbol, we see the atomic number at the bottom is 20, so there are 20 protons. Since the atom is neutral, it must also have 20 electrons. To find the neutrons, we subtract 20 from 40. This simple subtraction is the key to unlocking any isotope structure. Let us review the key takeaways from our first section on atomic structure. We have established that atoms are the building blocks of matter, composed of positive protons, neutral neutrons, and negative electrons. The central nucleus holds almost all the atomic mass, where the mass number equals the total number of protons and neutrons. We also learned that isotopes are variations of an element that share the same atomic number, but differ in their atomic masses due to their neutron count. Finally, we defined ions, which are charged particles that form when an atom gains or loses electrons, resulting in a charge. These four definitions form the foundation of chemical reactions. We can now answer our second essential question regarding the key discoveries of atomic structure. The modern atomic model evolved through a series of major breakthroughs. John Dalton introduced atoms as indivisible units. J.J. Thomson discovered negative electrons. Ernest Rutherford identified the positive nucleus. James Chadwick found neutral neutrons. And Erwin Schrödinger developed the probability-based quantum model. Each scientist built upon the work of those before them. This is how science works. Before we move to our next topic on the periodic table, please complete this brief exit ticket. It consists of 3 questions. First, name one scientist and describe their contribution to atomic theory. Second, describe where protons, neutrons, and electrons are located inside the atom. Third, explain how Schrödinger's quantum model changed our understanding of electron behavior. Take a few minutes to write down your answers now. Let us see how you do today. We are now beginning our second major topic, which is the organization of elements in the periodic table. Our first goal is to explain how the modern periodic table arranges elements based on their atomic number. Our second goal is to understand how knowing these atomic numbers enabled scientists to synthesize new elements. These targets will help you see the table as an active, predictive map. Let us begin. Let us look into our third essential question. How did the concept of atomic number revolutionize the classification of elements and lead to the creation of new ones in the laboratory? In the 19th century, chemists did not know about protons or electrons, yet they noticed that elements shared similar behaviors. They began organizing elements by their atomic mass. In 1864, John Newlands proposed the law of octaves, noting that properties repeated every 8th element, though this rule failed after calcium. By 1869, Dmitri Mendeleev and Julius Lothar Meyer independently discovered periodicity, which we define as repeating patterns in chemical and physical properties. This was a massive step forward for chemistry. Dmitri Mendeleev demonstrated the power of the periodic law by rearranging 17 elements based on their properties rather than atomic mass. He even predicted the existence and properties of undiscovered elements, which he prefixed with the Sanskrit word eka, meaning one. These elements were later identified as scandium, gallium, and germanium. In 1911, Henry Moseley made a monumental discovery that changed chemistry forever. He demonstrated experimentally that the properties of an element are determined by its atomic number, which we define as the number of protons in an atomic nucleus. Before this, chemists organized elements by atomic weight. Moseley proved that nuclear charge is the true organizing key. This breakthrough perfected Mendeleev's periodic table, which scientists at the turn of the 20th century hailed as the most predictive tool in all of science. Let us examine the modern periodic table in detail. The entire structure is based on the periodic law, which states that the properties of elements are periodic functions of their atomic numbers. This means that when we arrange elements in order of increasing atomic number, elements with similar chemical and physical properties repeat at regular intervals. This beautiful repeating pattern is why elements are grouped into vertical columns called families, which share characteristics such as chemical reactivity or electron configurations. This slide shows a key periodic trend, which is atomic size. When you look at the representative elements, you will notice a clear, repeating pattern. As you move from left to right across any horizontal period, the atomic size actually decreases. However, as you move down any vertical group, the atomic size increases. This trend is a direct result of how protons and electron shells change as atomic numbers increase. Mendeleev also predicted undiscovered elements. This same law enabled the prediction of noble gases, like neon and radon. In 1922, Niels Bohr predicted that element 72 would resemble zirconium, leading to the discovery of hafnium. Think about how a single table predicted elements that no human had ever seen. Let us explore synthetic elements, which are human-made elements that do not occur naturally on Earth. There are currently 26 known synthetic elements, including technetium, promethium, and various transuranium elements, which have atomic numbers greater than 92. These elements are produced in particle accelerators called cyclotrons, which speed up ions to high velocities. This process is called artificial transmutation, where one element is transformed into another. Despite their usefulness, synthetic elements pose serious risks if not properly controlled. They are highly radioactive and toxic, can ignite at room temperature, and may trigger chain reactions. Exposure to their radiation can cause severe health effects, including radiation sickness, sterility, and genetic disorders. Let us recap the main points from our section on the periodic table. First, elements are arranged by atomic number, which defines their chemical behavior. Second, the periodic law allowed scientists like Mendeleev to predict undiscovered elements long before their discovery. Third, understanding atomic numbers enabled the synthesis of new elements. Finally, while synthetic elements are useful, they are highly radioactive and must be controlled carefully. This summary is crucial. We can now answer our third essential question about how atomic numbers revolutionized chemistry. Organizing the periodic table by atomic number rather than atomic mass revealed the true repeating patterns of chemical properties in nature. This clear organization allowed scientists to predict the properties of missing elements. It also gave us a precise roadmap to synthesize new elements by targeting specific numbers of protons in nuclear reactions. To complete our lesson, please answer the 3 questions on this final exit ticket. First, name the scientist who introduced atomic number as the organizing principle of the periodic table. Second, explain how Dalton's atomic theory helped in identifying chemical elements. Third, describe how atomic numbers are used to create new elements in the laboratory. Write down your answers as a final review. This is the end of today's lesson.